Okay, so here, let's talk about how to, understand a simple linear regression for the CE sample. So this is really putting everything into context. And then we're gonna end today by talking about how to MC simulation using JAX for the simple linear regression model. So equation 8 and 9 is pretty much what we had done before for simple linear regression. We're having the yi's independently follow a normal distribution with mean mu I and sigma as the standard deviation. Equation 9 tells us how mu I is connected with xi. It is a linear combination of beta 0 plus beta 1 times xi. And for the CE sample, as we know, log expenditure is a continuous variable, which is the outcome variable, and log income, which is then is the y, and then log income is our xi, which is the continuous log income itself. Okay? So the intercept, if we put it into context over here, beta 0 tells us the expected log expenditure mu I for a consumer unit I that has 0 log income, meaning that xi is going to be 0. Okay? So that's a typical way, as we know, to interpret an intercept, but specifically in this context, it's going to be the expected log expenditure for a consumer unit that has 0 log income. The slope, beta 1, then will be the change in the expected log expenditure, which is mu I in our way, when the log income of the consumer unit increases by 1 unit. So this is very similar to what we generically say, the interpretation of beta 0 and beta 1, but in this particular context, which is what we also need to master, is making sure that you know how to interpret those parameters in context for a particular example. All right, so let's talk about how can we get priors. Okay, so beta 1, beta 0, and we know sigma as well. These are the 3 parameters that we need to give priors to. And just like before, let's start simple, assuming independence across all of them. And equation 10, in this case, as you can see, the joint prior for beta 0 and beta 1 and sigma. As of right now, we are breaking it into 2 parts and multiplying them together. The first part is having a joint prior between beta 0 and beta 1, and then another individual prior for sigma. And this is assuming independence, so we're able to break the joint into the product of 2 marginals, or I should say 1 marginal and another joint, because we have 3 parameters in total. So this is just a starting point. Okay. If you further assume independence between beta 0 and beta 1, okay, then I can further break the joint of beta 0 and beta 1 into the product of the prior for beta 0 times the prior of beta 1. And then specifically, we can give normal priors to beta 0 and beta 1. For example, if you're really not sure where the beta 0 and beta 1s are, you can center the normal priors for them as 0, and then give a really large standard deviation to allow all possible values, I would say, for beta 0 and beta 1. For sigma, we're also going to use what we are very familiar with, okay? So sigma is the standard deviation. 1 over sigma squared is the precision, and we can use a weakly informative prior, which, for example, like the gamma that we used to do. And then, for example, gamma 1, 1, I think that's the one that we have used before. So overall, all of this are very weakly informative, meaning that we don't really know where beta 0, beta 1, and sigma are, and we're letting the data to drive the inference. So we're giving very weakly informative prior for all of them. And the reason why we use them, like the normal here, and gamma here, is once again, we are having our general model as normal beta 0 plus beta 1 xi, and then sigma, okay? So at the end of the day, the basic model is a normal model. Okay? When the basic model is a normal model for the standard deviation, as we know, the conjugate prior that we worked before is for the precision to be a gamma. Okay, so this is a very straightforward prior that follows from what we had done before. And then in the mean, for a normal model, we know that the conjugate for that is going to be another normal. Okay, so when you have a normal data model, the mean, if you want, you can give it a conjugate prior of normal, and that translates into a normal prior for the intercept and another normal for the slope. So from your probability course, in the past, you probably hopefully remember that when you have two independent normals, the sum of them is another normal. And that's the rationale of why when we are having the mu I, hopefully to follow a normal distribution, that translates into independent beta 0 follows a normal, and the other independent beta 1 times xi follows another normal, and then they're independent from each other. So when you add them up, they are the sum is another normal. Okay. So that's why to start with what we know in the past and translate those knowledge and skill into the current setting, we're giving a normal for beta 0, we're giving another normal for beta 1, and we're giving a gamma for the precision, which is 1 over sigma squared. And we call all of this weakly informative priors, meaning that we don't really know where the beta 0, beta I, and also beta 1, as well as the 1 over sigma squared to be. So we're giving a very vague prior, meaning that we're going to let the data to drive the inference. All right. So if all of that makes sense, if anybody wants to attempt to derive a full conditional posterior distribution or use this as an exercise, one thing we could do is, well, for the sampling model, we know that each of the yi independently follows a normal with mean beta 0 plus beta 1 times xi, and with a standard deviation sigma. So following the normal density, you can write out the joint likelihood. Okay, all of them are independent. So this is maybe one last time that we're looking at this kind of exercise. When they're all independent from each other, we're simply producting all of the density. Okay, so from I from 1 to n. And then in each of this, we're having a specific normal with mean beta 0 plus beta 1 times xi. So that's why it's yi minus the mean squared divided by whatever that we need for the normal density. And then if we remember what we have done in our mean Bayesian inference for a mean unit, you can do some simplification. And then this could be the level of simplification that you can do for the joint likelihood. Yes.
If we're using the priors, just
Yeah.
to go back a little bit, like with the parameters for this, we're just intentionally picking something that's kind of vague, and then it won't influence a lot.
Yeah, that's true, right? So you could have other priors going on. And in fact, the last lab 5, we're gonna introduce a way that, well, if you have certain belief or certain prior knowledge about certain things, maybe instead of this vaguely informative prior, like super wide normal that we're going over here, you could give other types of prior to represent your prior belief. But you're right, as of right now, we're using this vague or weakly informative priors just to get started, if it is indeed the case that you don't really know where the parameters are. But you could know from previous knowledge or study, and then there will be ways that we're going to cover, in this case, through lab 5, to let you see how you can give specific priors in a different context. Yeah, thanks for the question. All right, so here we are with the joint likelihood. And then, of course, we have our joint posterior, if you want. So I'm just writing out everything generically without the vague prior that we're talking about. And this could be, like I said, one extra exercise if you ever want to make sure that you are able to get the joint likelihood, get the joint prior, and then get the joint posterior accordingly. So I think it is possible to further simplify and try to recognize full conditional posterior distributions because we're using contiguous priors everywhere. Okay. However, just like I said, starting from hierarchical modeling here as well, we're going to rely on JAX to perform the MCMC for us. So then, of course, the key is making sure that you can write out the JAX code correctly, efficiently, to represent the exact model that you're dealing with. So I think that will be what we're going to talk about next.